in general, we have n features. So in that case, you will have a linear combination of them. Here, you have theta 0 for intercept, and you have the coefficient for each individual features here. So that's why you have theta 1, theta 2, up to theta n times xn here. So that is the parameter you have here. Okay, so what I'm going to do here, I'm going to use slightly, and then so overall, we're going to use linear algebra notation to represent these guys here. Instead of writing down linear combinations of features in this way, you can write them more compactly to be equal to theta 0 times inner product between theta and x here. So you assume theta to be a vector here, and you assume x is a vector as well. Okay, but well, I'm going to use slightly different notation from the slides here. So I can assume theta here to be a column vector with theta 1, theta 2, and theta n here. So it'll be a column vector here. Let's make this a slight change of notation here because this is more conventional. I'm going to assume x here is also a column vector, x1, x2, and xn here. So then the linear combinations of theta dot x here, you can simply write that as simply theta transpose times x. So you get the product between a row vector and a column vector. So that gives you a scalar. Okay. So in the end, my predictions here is simply to be theta 0 plus inner product between theta and x. So that's in general forms of linear regression here. So the number of parameters here will be n plus 1 here, 1 corresponding to the bias term of that. So that will be most general form. However, in these forms here, I have to write down them, I will specify the bias term specifically. So to simplify the notation here, people typically introduce a notation, convenience for introduce a notation such that make the notation easier. So the way how they did it here is this. So remember that I have this x vectors here. So I'm going to put a 1 here in this x vector. As a result, I have new vectors here. The first component is always a constant 1. Okay, but as a result, that my vector becomes n plus 1 dimensional because I have one additional component added on top of the existing ones. So and then I can augment my theta parameter such that the first one is theta 0. And as a result of that, again, I have an n plus 1 component of that. Okay, so that will be a notation here that we're going to assume we take this type of assumption. So this type of feature is called augmented features. We're going to put a constant augment the original features with additional 1 feature, and that's a constant 1. So now with this new annotations here, so my linear models here can be simply write down as just simply the dot product between theta and x here without the bias term. So the model itself does have bias. Just use this trick of notation here I introduce into this part of them. Okay, so we're going to make the assumption from now on. In any case, when I write down, say, I'm going to model here to be theta dot x here. So don't ask me where is the bias term. So bias term is already being considered within absorbed into the parameters and features here. So we do have a bias term within that. But in some other context, we want to make it specific. And in that case, we will write them in this explicitly in this form. So depend on different context. So bottom line is when we think about linear models here, we always have the bias term within the models. That is already taken into account. Okay, no matter whether I written in this form or this form. All right, just a notational explanation here. All right, so now here I have this complete this part. I have the data here. I have the model here. So y here at equal to theta dot x here. And then I need to think about the evaluation metric here. What is the performance, to evaluate the performance? So there are many ways for evaluate the performance of between prediction and the ground truth y here. There are many ways for doing it. So I'm going to introduce one metric, something called a MSE, mean squared error, for measuring the evaluation performance of linear regression models. So that was demonstrated in the following here. And this is the x here. And now remember that each dots here, this correspond to the observations here. So suppose I focus on this x here, And this is my observation, observed values, because this is corresponding here. This is my target values, all observations here. And then if I choose a line with this particular choice of theta 0 and the slope of theta 1, and then this is my predicted value. That's the y hat, because this will be predict based on the line here. That's my prediction. You can see there is a difference between my prediction and line, my actual target here. This is the error. This is a prediction error. They're not the same. And sometimes we call it a residual here. The y hat minus y is residual, right? Or y minus y hat, doesn't matter, right? So, so that's, we're gonna calculate residual for each individual dots here. So that's represented by this vertical blue lines here, this lines here. The larger this gap, the higher the error is your models. And you can see that those gaps are different for different dots here. Some of the dots here are doing pretty well, and the residual is small. For some of them, the residual is large. When I say residual is large in an absolute sense, okay? And then, in order to minimize, you want to identify parameters to fit the data. You can see that the best models here is try to make sure that the residual is small for all dots, for every training data set, every samples. So the way we're doing this, we're going to do an average of a squared residual of each data set here. The give a measurement of the collection of the entire training data sets here. So what I mean here is this. So now for each one of them here, and I use the notation I'm referring to. So I have, this is my target value for the I sample. This is my target value, this observation. And this is my predicted values here for the I samples of that. And I take difference of them, that's the residual. And because I care about the absolute values of residual instead of the signs of that, I take squares of that. So this is measures the overall, the errors corresponding the I samples of that. And if I want to combine all entire training data, I take an average of these guys here. Summation over I goes from 1 to n. M is the total number of samples. And divided by n, I get the average of squared error. And that's something called MSE, mean squared error. And that's calculated in this way. So remember now, this predictions here is a linear model prediction, is dot product between theta, this parameter, and the input xi here. So that's my prediction, okay, based on the linear regression models. And now if you have parameter theta here, you can plug in, you can calculate this, the residual between y and y prediction and the ground truth. Okay, so that's a linear regression model. So now let me actually